All right, so good morning. We'll go ahead and start class today. I'll be using just this board right here, and I'll record that. So we'll continue in chapter 3. By this point in time, you probably should have worked your way through the reading of chapter 3 and started your homework problems. And so the next homework will be due on Friday, February 3rd, so that's going to be a week from Friday. So be sure that you're working through those problems. Those are in D2L, so everybody should have access to those. Are there any questions about the problems or the reading so far out of chapter 3? Does anybody have any questions? Okay. So we'll continue then with point groups. So last time we were talking about the D point groups. So the purely rotational point groups would be Dn, where the only symmetry elements present are the rotational axes, and there must be an n-fold principal axis and then n number of C2 axes perpendicular to that n-fold axis. Okay? And then we have the DNH point groups and the DND point groups, which of course have horizontal mirror plane associated with them, and then vertical mirror planes associated. And the presence of those could generate still more symmetry elements. So let's just complete our discussion of the DNH and the DND point groups today, and then we'll move on from there. So the DNH point groups might be represented with the example that I showed last time at the end of class, a paddle wheel or a type structure. Another type of common structure would be sandwich type structures. So if you imagine maybe a metal with a four-membered ring bound to it, and then another four-membered ring bound to this, that these are eta 4, let's say. Right, so then if these are eta 4, we have simultaneous bonding to the atoms and the ring, so sandwich structure. Right? So if we have such a sandwich structure, this would be a view sort of in between the slices of bread, if you will. We could also imagine a view from the top, in which we would see the four-membered ring as a square set of atoms. The metal would be below that, and then there would be another four-membered ring of atoms directly below. So this would be an eclipsed conformation. Okay? So specifically in that eclipse conformation, we would assign this to DNH point group because of the following symmetry elements. So there should be a C4 axis which goes through the centers of these four-member rings and contains the metal atom. So that is the C4, right? And that is the highest order principal axis of rotation. I need to make an adjustment to my computer because it has a screensaver mode, and I don't want that to cancel the recording. So I'm going to make a quick adjustment here on the Mac, desktop screensaver. Sorry about that. No, that's going to be under power management. Why am I not seeing this? Because it's in class. That's why I'm not seeing it. Okay, that should work now. Hopefully my computer will not stop in the middle of the recording. Okay, so continuing, we've identified the principal axis of rotation. For this to be a D point group, there must be n number of C2s perpendicular to that. Can we identify those? So now that we're looking sort of through this CN axis, we can easily identify the C2s that are perpendicular. So for example, there would be a C2 that contains the metal and would be going through the edge centers in this eclipsed view. So when I rotate about the C2 axis 180 degrees, the top ring and bottom ring basically exchange positions, the metal stays in place. And there's another such C2. In fact, if I use the C4 symmetry operation and perform a 90-degree rotation, I see the symmetry equivalent C2 axis. So that will be perpendicular to the first and perpendicular to the C4, right? So in fact, this is a way to identify symmetry operations that are in the same class in the group, if they're generated by another symmetry operation in the group. So that's kind of interesting. Now there are two other C2s perpendicular to the C4, and those go through the metal atom again, but now they are, in this eclipse view, are beneath the corners of the four-membered rings, right? So that when you perform that C2, again the rings exchange, but this corner will move to this side on the bottom now, okay? And then again, the C4 operation, by performing a 90-degree rotation about the C4, generates the second C2 of this class, basically, which goes like this. So now we've identified the four C2 axes perpendicular to the C4, which by definition makes this a DN or a D4 type of a group. But we have the additional symmetry element of a mirror plane of reflection perpendicular to the C4, so that will be our sigma H, which makes this a DNH point group. So that mirror plane, of course, is the plane that contains the metal, is in between the two four-member rings in the sandwich complex. They're all parallel planes here. So whenever you identify the reflection plane perpendicular to the principal axis of rotation, it is a DNH point group. All right. In addition to that, we have several other symmetry elements. And last time we identified that there's an inversion center here. Okay. We also identified a improper axis that is superimposed with the C4 axis. So there's also a S4 axis. So in this sandwich structure, if we label these atoms 1, 2, 3, 4, and then 5, 6, 7, 8, let's say, if we perform an S14 operation, then carbon atom 1 will move by 90 degrees and then reflect about the plane perpendicular to the C4 and will move to the position of C6. right? And so on. So there is an improper axis of rotation that generates symmetry equivalent images. And the two symmetry unique operations are S14 and then S34. There are also mirror planes that are perpendicular to the sigma h present in this point group. And those are basically defined by they contain the C2s and the C4. Right? So you can pick any one of these four C2 axes, and then you take the C4 and use that to define a mirror plane. Okay, does that make sense? So there will be a mirror plane here, a mirror plane here, a mirror plane here, and a mirror plane here as well. So we have four mirror planes. Now those mirror planes are also in symmetry classes, because if I take this mirror plane, which contains this C2, right, and if I perform the C4 symmetry operation, it rotates to this position, which now is the other mirror plane. So those two mirror planes are in the same symmetry class. They're symmetry equivalent. Okay? Those mirror planes, we can arbitrarily assign those to lying on Cartesian coordinates. And you can give them a hierarchy. And because you might decide to call this direction X and this direction Y, we would certainly call this direction Z by convention to align that with the principal axis of rotation. But if we did say that this was the X direction and Y directions here, and since those mirror planes are on those axes, the XZ and XY planes, we'll go ahead and call those sigma V as vertical planes, just for purposes of assigning a designation of those planes, and unique from the other set of planes, which are also in the same symmetry class because the C4 operation generates the other, right? And so because those planes are bisecting our coordinate system, we can call these sigma D as dihedral planes. So we'll just call these vertical, and these will be dihedral. Okay? So then all of the symmetry elements present include E, the C4 axis, which generates, of course, the C14, a C24, and then a C34, right? We have four C2 axes, right? Notice this C2 axis is different than the C2 that is superimposed with the C4, okay? And then we have sigma H. We have an inversion center present on this metal in this example. There are four vertical planes, but we assign those to unique classes. And I should go ahead and actually split these into symmetry classes based on whether those axes were in the X or Y axes, or if they bisect X or Y. We have four mirror planes perpendicular to sigma H. So two of those are, we call them sigma V. They're in the XZ and YZ plane. And then two of those are dihedral planes that bisect the X and Y axes. All right. Then we have the improper axis of rotation, S4, which generates S14, S24 is inversion. Wait, no, it's C2. Right? because they're going to rotate 90 degrees, reflect down, rotate 90 degrees again, reflect up. So the two reflections cancel. The net is a 180 degree rotation, or C2. Then we have an S34 and an S44 is identity. This S24 or C2 is equivalent to this one here. So altogether, how many symmetry operations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this constitutes a group with 16 symmetry operations, or 16 elements. So the order of the group is 16. Okay. That's a D4H. So that should give you a good idea how the DNH groups work. Now we can move to DND groups, unless there are any questions about this. Okay. So let's erase that. So for D and D, we could take the same molecule, in fact, but imagine a different conformation where instead of eclipsed rings, you have staggered rings. So if I just redraw this four-member ring on the top of the sandwich complex, eta 4 to some metal, and then another four-member ring, eta 4, but now it will be rotated by 90 degrees. So we have the staggered sandwich complex. So if we look through the centroids of the four-member ring and the metal along that axis, you should see something that looks like this. So here's the four-member ring on the top, the metal is in the center, and then the four-member ring on the bottom, like this. Okay, so we have our staggered sandwich complex. All right. So then what kind of symmetry elements and operations can we locate within this molecule? So first, anytime I'm looking at these, I want to look for a principal axis of rotation so I can sort of orient the whole system relative to a Cartesian direction Z, assign the highest order axis. So I want to look for that first, right? And so there's clearly this sort of fourfold symmetry to this, right? So looking through here, I have, again, a C4 axis, right? So if I perform the 90-degree rotation about that axis, the top four-member ring rotates onto itself. We just exchange corners. The bottom ring also rotates onto itself and exchanges its corner positions. The metal stays in place. So the C4 axis is in place, and that will be the highest order axis, the principal axis. Okay. I'm illustrating a D in D point group, so there better be 4 C2s perpendicular to that C4 in order for this to be a D4D. So do we agree that those exist? All right. So remember before I drew an axis that sort of ran parallel to these edges of the top four-member ring. If I put a C2 right there, the top four-member ring rotates to the bottom, but it will not be superimposed here because this is rotated by 45 degrees relative to the first. So that cannot be one of the C2s. Where is the C2? And maybe I didn't draw this very precisely. Let me just edit this a little bit, because I think I can improve my drawing. I want to look at this halfway point here. At this halfway point here. This point here. And this point. That looks a little bit better. All right. Can I take an axis like this and perform a 180-degree rotation? So I cannot go into a C2 that would be eclipsed with the corners of the bottom four-member ring and passing through the middle, I guess, or just below the middle of the top four-member ring. That won't work. So I cannot use the same C4 axes that I drew in the D4H case. Now, the C2s go exactly in between where these cross over above and below each other. So when I perform a 180-degree rotation, this point swings around to the bottom at this symmetry equivalent position. Right? This position here is going to swing around to the top to this position. Okay? So that is the C2 axis. Now you might imagine if I perform a C4 operation along this axis, then I generate the perpendicular C2, which goes like this. See that? And then there are two other C2s which bisect the angle formed by these perpendicular C2s. And they are in a different symmetry class, right? So we might call this C2 prime just to indicate that those are in the same class. And then the other C2s, one being here, we might call that a C2 double prime, just to indicate the different class, because the C4 does not generate this C2. But the C4 will generate the other symmetry equivalent C2 right here. Okay. So indeed, we do have 4 C2s perpendicular to the C4. Does that make sense? So that will always hold true for any DND point group or any DN point group. Okay, so this molecule does not have a mirror plane that's perpendicular to the principal axis that is a reflection plane as a symmetry element, right? In the eclipsed conformation, I could draw the mirror plane through the metal, and the two rings are symmetry equivalent. They reflect into each other. But because these are offset, that's no longer true. So it's not a DNH point group. Are there other mirror planes present in this molecule? And so this time, you can draw mirror planes that pass through, let's say, any two corners, opposite corners, of one of the 4-member rings. And I could use a different color to illustrate those vertical planes. So if I draw plane that is perpendicular to the board. It's coming towards you and going away from you. Can I perform a reflection and generate the symmetry equivalent image? Right? So in the top ring, this reflects about the plane. This corner to this corner, these points stay in the same position. The metal stays in the position because it's in the plane. And in the bottom ring, these corners exchange, these corners exchange. Right? And then if I perform a C4 operation, I generate the symmetry equivalent mirror plane perpendicular to this, like so. Right? And then you can generate two other symmetry equivalent mirror planes. By similarly going through corners, say of the bottom ring now, and then the corners this way, so it's perpendicular to the first. All right? So now we have 4 mirror planes. Is there an inversion center? No. Because if I invert this ring, I should generate an eclipsed ring below, but they're staggered. So there's no inversion center. Is there an improper axis? Yes. There's an improper axis superimposed with the C4. And now, what order is this axis? This one's interesting because I can rotate. Let's say I'll start with this corner on the top. If I rotate by 45 degrees, the top square then moves to a position that would have been eclipsed with the bottom square, except that bottom square is also moving along, right? But then I performed a reflection about the plane perpendicular to the axis, so this point is now brought to the bottom square. So 360 over 45 is 8. We have an S, that was a terrible 8. We have an S8 improper axis. So the S8 generates S18, S28. The two reflections cancel, so this is the net of a C4. Right, for a C1 port. We have an S38. That's a unique symmetry operation. We have S48. So 4 reflections cancel out. This is a C48, which is a C2, which is in this direction. Then there's S58. S68, which is equal to C34, and then S78 is unique, S88 is equal to identity. Okay. Any questions about that? All right. So now we've covered low symmetry groups. We've covered CNH, CNV, D rotational groups, DNH, DND. And there are still other point groups to think about. Let's look at those. An unusual point group are the S point groups. They're not very common, but they do pop up on rare occasions. And the S point groups they only appear to arise for even numbered n. And so it's basically a lot like a rotational C point group, except you might generate an inversion center when n over 2 is odd. So, for example, the S4 point group has the symmetry elements identity. There's an S4 axis, and then an S4 axis, of course, generates S14, S24, S34, S44 is identity. So this looks very much like a cyclic point group. And then the S24, of course, is equivalent to simply C2. So we see E, S14, C2, S34 as the unique symmetry operations that are the elements of that point group. Okay. If you go to an S6 point group, then you have the identity. We can just write the S6 symmetry element generates the following symmetry operations. S16, S26, S36, S4, 6, S5, 6, S6, 6. Right? So S16 is a unique operation, rotate 60 degrees, reflect about the plane perpendicular to the axis. And S26, the two reflections cancel, so this is equivalent to a C13, right? And S36, you have three reflections now. So I've rotated 180 degrees and reflected about the plane perpendicular. What is that? So this would be a C2. And then reflection in the XY, about the XY plane. If I multiply these together, what is this? Inversion. So whenever you have an improper axis where n over 2 is an odd number, so 6 over 2 gives you 3, that's odd. It means you have an odd number of reflections, but n over 2 gave you the 180 degree rotation. You have this problem here, which means this will always be inversion. This is a C2, 3. This is unique, and then this is identity. So the elements of the group are identity, C13, C23 inversion, S16, S56. Okay? So that's an S point group. And now we have the very high symmetry groups. So you were looking at product tables for groups with 8 elements, and I showed you a group D4H that had 16 elements. There are still bigger point groups. Right? So we already identified 2 groups, or I guess 1 group, that had C infinity V, which had an n-fold axis where n was infinity. I could rotate by any infinitesimal amount and generate a symmetry equivalent image. So C infinity V examples would be something like carbon monoxide, hydroxide ion, any sort of asymmetric linear molecule, a cone would be C infinity V, right? There's another group, D infinity H, where you have a symmetric linear molecule. So examples would be nitrogen, right? Hydrogen, whatever you want, or a cylinder. These would be examples of D infinity H symmetry. So you have the Cn axis, n equals infinity, and you have an infinite number now of C2s perpendicular, and there's a sigma H perpendicular to that principal axis. So we have those infinite type point groups. Another one is the tetrahedral, or the cubic groups, let's say. Cubic groups. So we have tetrahedral and octahedral point groups related to these platonic solids in different ways. And these are solids that can be inscribed in a cube and are related to the symmetry of a cube. Okay? So let's start with tetrahedral type systems. The molecule methane is obviously tetrahedral and symmetric. What are the symmetry elements? There are a lot. All right? The order of the group is going to be 24. So imagine having to write a product table with 24 elements. Right? It's a lot of work. What's the best way to do this? We can inscribe this in the cube. I think that helps us to see some of the symmetry elements. And then we'll look at the threefold symmetry. Right, so if I take my center points here, so here's the carbon. I'll take 2 hydrogens out here, and then 2 hydrogens here, so that this diagonal is perpendicular to this diagonal. Okay? Then, of course, we have the threefold view through any one of the CH bonds. And if I decide to use this cube even, I could take this point as the closest point to the eye and look through this point to the carbon, to the hydrogen, so that we're looking through the CH bond and it's going behind you. Right? So if I do that, I'll draw a hexagon as a shadow. That hexagon will be split into 3 equal sections. Right? So this point is here. And then the carbon is exactly in the middle. The hydrogen is beneath it at the intersection of these back edges. And then the 3 hydrogens at these corners are here. Right? So now we can start picking out the symmetry elements and the symmetry operations they generate. All right. So in this view, we can take an axis that traverses the center of this face of the cube into which the tetrahedral molecule is inscribed. It passes through the center, which has the carbon atom in this case, and then through the edge center that's opposite on this cube. Does that make sense? This is a C2 axis in the system. If I just take this square face, if I perform a 180-degree rotation about the axis I just drew, those 2 hydrogens exchange position, as do these simultaneously. And this remains unchanged because it's in the axis. And it turns out there are 3 mutually perpendicular C2s. They all pass through the center, in this case, the carbon atom. Right? And then there's one that passes like this. If I were to look at this cube directly face on, I would be looking through the other C2 axis. So we have 3 C2 axes. Are there any mirror planes? So it turns out any 2 of those C2 axes can be used to define a mirror plane, a reflection plane in this molecule. So if I want to call this one, for example, C2X, and call this one C2Y, and this one C2Z, right? If I take the XY plane, so that's the flat plane here that cuts it in half this way, is that a reflection? No. That's not a reflection because it would take these 2 here and these 2 here. That's not symmetry equivalent. But if I take a plane, maybe I need a different color to illustrate this a little bit more easily. If I take a plane that splits this face and contains these 2 atoms and the carbon, notice that bisects the C2s. So I was just about to trip myself up. I was about to say that any 2 C2s make up a mirror plane, and that's wrong. In fact, the mirror planes bisect the C2s. So didn't mean to confuse you. But I think you're able to see it because these hydrogens and this carbon are in the plane, so they don't move. And then these 2 exchange position upon reflection, right? And I could draw a similar plane perpendicular to this, or have a similar effect now if this plane, the 2 hydrogens at the top and the carbon remain in place, the 2 hydrogens here exchange. Now what if I do something like this? I draw a mirror plane now that splits this face in half by passing through the face center and then contains these two hydrogens like this. It contains the carbon atom and these two hydrogens, so those remain in place, but then these two hydrogens are reflected, right? So I could draw one plane like that. It crosses these opposing faces of the cube, these parallel diagonals. And then I could draw a plane perpendicular to this. Right? Now that plane contains these two hydrogens and the carbon, so they remain in the plane upon reflection, but then these two exchange. All right. And then I could do the same thing. So I've already drawn two planes that cross perpendicular diagonals on the parallel top and bottom faces. I've drawn two planes that are perpendicular on the diagonals of these two opposing faces. I could do the same thing for the front and back faces. I could draw a plane that connects these two hydrogens and goes along the diagonal to the back. Okay, so this CH2 is unchanged. These two hydrogens exchange. And then I could also draw the plane that goes on this diagonal and the back diagonal this way. So there are 6 reflection planes. And maybe an easier way to visualize that is remember this view of the tetrahedron or the tetrahedral molecule. If I look along any one of those CH2 wedges, edge on, such that one is coming towards you, one is going away, I have a mirror plane here and here. That's really easy to see, right? It's probably easier to see than this view. And if you imagine that the tetrahedron has 6 edges, and each one of those planes is basically an edge, you'll see that you have 6 sigma planes of reflection. Now you can go to the threefold view. I've only got 2 minutes, so I'll hurry this up. It's very obvious that there should be a C3 axis because the 3 hydrogens can rotate into the positions of the other hydrogen, right? So this is the C3 through here. But there are 4. You notice that the C3 contains the CH bond that's pointing away from you. There's a hydrogen hidden behind this carbon. So that's 1 CH bond. I have 4 CH bonds in the molecule, so there are 4 C3 axes. They simply go from opposite corner to opposite corner in this cube, where they pass through one of the vertices of the tetrahedron. Right? Each C3 axis I could rotate clockwise, or I could rotate counterclockwise. The counterclockwise would be the same as rotating clockwise twice. So each C3 generates 2 unique symmetry operations as elements in the group. There's no inversion center for the tetrahedral case, but we do have another type of symmetry element, and it's an improper axis. Okay? In fact, we have an S6 superimposed on the C3. And you can see it in this view again. If I rotate, oh wait, do I have an S6? No, there's no S6. I'm thinking of something else. So there's no S6. What there is, I was tricking myself because I was thinking about octahedral. What there is an S4. Okay? So notice I can rotate by 90 degrees. This hydrogen moves towards you, but in the right orientation. And then if I perform the reflection about the plane perpendicular to the S4, it now goes away from you. So we have S4s that pass through the centers of these HCH angles. So I think I've got that. That should be everything. Altogether, there are 24 symmetry elements. So we have the identity, 3 C2s, 6 mirror planes. We have 4 C3. Each one of these generates C13 and C23. And these are grouped together in the same symmetry class. We'll demonstrate that at a later class. So they're all together 8 symmetry operations that are unique. So that gets us up to 4, 10, 18. And then the others are the S4s. There are 3 S4s because we have 6 edges of the tetrahedron, and each S4 goes through the edge centers of opposite edges of the tetrahedron. So it contains 2 edges. 6 over 2 is 3. So 3 S4 axes. Each one of these generates a unique S14 and an S34. So altogether, 6 symmetry operations. The S24, of course, is the same as the C2. So 24 symmetry operations. The order of the group is 24. This is the tetrahedral point group. It has the symbol TD. So that's a good stopping point because I'm out of time. We can talk about the octahedral point group on Friday. Look through the questions, look through the text. If you have a question or something you're unsure about, bring that to class Friday because that's the last class time I'll spend on chapter 3. We'll start moving into chapter 4 next week on the 30th. All right? Thanks.